Okay, so my plan for today was to go over some of the problems from the homework, but it seems you guys have solved them. So we'll start with some of the harder problems. But actually, maybe I'll ask, is there anything you wanted to go over from the homework? Anything in particular? Either of you?
No.
For me, maybe problem 4 or 5 from the geometry.
I see. So was there a problem five? I don't think there was a problem five.
Yeah, it was from IMO 2022.
Oh, okay, so that's problem four. Okay, good. So
Yeah.
that one, let's go over that one at the end. Okay, so that one, yeah. So I knew that one was hard. Let's go over that one at the very end. Um, but yeah, okay. So then let's go on with the number theory problems that I have planned. Then at the end we'll go over these the hard one. Okay, so let's see. I need to share my screen. Um, okay, let's see. Yeah, so this was my plan for today to do some of these. Um, yeah, so maybe let's as a warm up we can start with the first one. Um, yeah, so um, actually maybe I'll skip this one. I'll leave that one for. So let's start with the second one. Okay, so let's start with the second one. Um, I also so this is the problem. It's from the short list. It's yeah, so this is from the IMO short list, and the problem is so you want to find all pairs of positive integers so that this equality holds. Okay, so maybe why don't you take a few minutes to think about it, at least 5 minutes, and then we'll collect some ideas. Okay, so let's reconvene. Maybe what are some ideas or some observations you've made?
Um, I was thinking of using Legendre's formula.
Okay, so what is
Uh,
Legendre's formula?
Um, so we can take the the common factors, the twos, and their number should be equal to k divided by 2 floor plus k divided by 2 squared.
Good. So yeah, okay, that's good. So right, so we should use Legendre's formula, but let's first say what the idea is. So yeah, maybe we'll. So why do we use Legendre's formula? Well, the point is count twos in the prime factorization. So that's the idea, right? If the two numbers are equal, the number of twos in the factorization should be equal. And now, what is this Legendre's formula? It tells you the number of twos in k factorial, right? And so, what is that? Yeah, so let's write it down. We use this notation. We write nu 2 of k factorial. So this notation, it means number of twos in prime factorization. And so there's a formula, and it says that it's equal to k over 2 plus k over 4 plus k over 8, and so on. And so the bracket means floor. Um, so Abdullah, do you know this formula? Have you encountered it before?
I've encountered it, but I haven't studied it.
Okay, so maybe let's give an argument of why it's true. Um, so how do we count the number of twos in k factorial? So k factorial is 1 times 2 times 3 times 4 all the way to k. So the first thing, we want to know how many twos there are at this product. So the first thing we do is we count the number of evens. Okay, so for every even number, so for 2 and 4 and 6 and so on, it'll contribute 1 power of 2. So number of evens, well, what is the number of evens? We should divide by 2 and round down, right? That's what the number of evens is. That's k over 2. But now the problem is some numbers will contribute more than 1 power of 2. So for example, 4, 8, 12, 16, all the multiples of 4 will contribute an additional power of 2, right? So um, let me, oh, yeah, so the number of 4s will be k over 4. And each of those, they'll contribute one extra multiple of one extra power of 2. And then so on. So then the number, and then each multiple of 8 will contribute a further power of 2, and so on. Does it make sense, Abdullah, the
Yeah,
argument?
yeah, it makes sense.
Okay, good. So yeah, so that's a very good formula, and it will work with any prime, not just 2. You can count the powers of anything. Um, great. So that tells us the number of twos in the prime factorization of the left-hand side. So now, of course, we should try to count the number of twos on the prime factorization of the right-hand side, right? So what will that be? How many twos will we see on the right-hand side? So I guess, yeah, what are we asking? V2 of the right-hand side.
It's the sum of all numbers from 1 to and minus.
Right,
So we
so
get
wait. Right, great. So right, so we should get something like this one will contribute nothing, and then this one will contribute 1, and then this one will contribute 2, and all the way to this one. Last one will contribute 2 to the n minus 1. Right? So the total that we get will be 1 plus 2 plus all the way to n minus 1, which is n times n minus 1 over 2. Okay, great. So now what do we do with this? We've counted the number of 2's on each side, but now how do we actually proceed with the problem? So maybe one point is certainly these numbers are equal. Okay, so we must use this somehow. So this is a very common thing in number 3, Olympiad number 3 problems, right? We do some kind of number theoretic calculation, like we look at primes or divisibility or modular arithmetic, and we get some number theoretic information. But then we have to use that number theoretic information to do some kind of maybe inequalities or something, right? Because the way these problems usually work is you get some information from the number theory, and then you get some different information from inequalities, and there's a tension, right? So let's see how this works. Um, Good. I don't know how to paste. Let's see. Okay, that's okay. Let's just recall what we had. So what we had was v2 of k factorial was this guy, and v2 of the right-hand side is n times n minus 1 over 2. So the point is, we want to use this to compare k and n. So what comparison can we get? Well, the first point I'll make is that, you know, this expression here is a really, it's not a nice expression to work with. Is there there's something we can do that's better? Like maybe there's some nicer approximate expression. Do you guys understand what I'm asking? It's not a great expression to work with.
Maybe we can remove the floor functions. So we have an equality that's inequality that's greater than or equal to.
Great. So yeah, so the point here is we can write n times n minus 1 over 2. Instead, we put greater than or equal to, and we remove the floors. Good. And now what is this equal to? Well, we can factor the k, and now this is a classic geometric series. This is just k. So the point here is, point of all of this is that now k is greater than or equal to n times n minus 1 over 2. And so this is the key information we get from the prime factorization information. Now, how can we use this to solve or at least to make progress on the problem? So remember, the thing you should think, right, when you have some kind of inequality like this, okay, we got this inequality from the number theoretic information, right, from the prime factorization. But now we think, is this even possible, right? If we look at, k has to be like pretty big compared to n. If k is that big, could this kind of a relation even be true, right? Like, does the inequality somehow force k to be so big that that expression just cannot be true? Right? Does it make sense what I'm saying?
Yeah.
Yes.
So maybe we substitute k for an equality.
Great. Yeah. So if it's true, right. So I can start a new page or something. Um, so I just want this information, right? And the idea is, yeah, now I want to say if there is a solution, it actually implies that n times n minus 1 over 2 um, uh, factorial is less than or equal to 2 to the n minus 1, 2 to the n minus 2, all the way to 2 to the n minus 2 to the n minus 1. And now let's think, is it possible? So here's something, you have just some kind of estimation, right? So from your intuition, which of these sides should be bigger, right? Because if we can say that the left-hand side is bigger, then we're done. There's no solution, right? So which side do you think should be bigger?
Left-hand side.
Yeah, and so why is that? So first of all, let's be clear when I say bigger. So if n is small, like if n is 1, for example, um, then certainly it's maybe it's not, or maybe it's okay. If n is 1, it's maybe equal, right? So for n equals 1, you get 0 factorial, which is 1, compared to 2 to the 1 minus 1, which is also 1. So and for n equals 1, they're equal. For n equals 2, it's like, I guess it's again 1 factorial, and compared to 2 to the 2 minus 1 times 2 minus 1. So, okay, for small n, maybe the right-hand side is bigger. But yeah, we're saying for large n, so large n, which one is true? And you're suggesting, Abdullah, that maybe the left-hand side is bigger. And so what is your intuition? Why do you think that's true? Maybe you can give some kind of light argument?
Um, Maybe because of how the factorial function grows over time.
Yeah, so
But
okay.
yeah,
Go ahead.
I don't really have a good argument.
Okay. Yeah, so the factorial function grows quite fast. Now let's be a little careful, right? So if instead it was n factorial, then what would the answer be? Like between n factorial on the right-hand side, which one is bigger?
Probably the right hand side, yeah.
Yeah, probably the right-hand side because you can write this as 1 times 2 times 3 all the way times n. And now you can compare term-wise at least, right? The right-hand side is bigger term-wise. Um, like this one exceeds this one, and this one exceeds this one, and so on, right? So, okay, at least so you have to be a little bit careful. So why might this expression be bigger than this expression? Any ideas? Maybe there's some way to group the terms on the left so you can compare them directly.
Are we talking about n factorial or n times n minus 1,
We're
like
talking about
also
this one, n times n minus 1. Right? Because for n factorial, we know the answer. For n factorial, we know it's smaller than the right-hand side. So for this one, n times n minus 1 over 2 factorial, how can we compare? Yes, maybe let's yeah. So our conjecture is that right-hand side is bigger. Right? Why? Um,
You mean the left hand side?
sorry, yes, you're correct. I meant the left-hand side. I wrote right-hand side. The left-hand side, yes. Hello, Karam. We're working on this problem at the top of the page. Um, sorry, we're quite far in it, but maybe at the end I can catch you up on what we thought of it. So yeah, maybe so the idea should always be something like, what are we doing here? So we're multiplying several numbers on this side. Um, let's see. Can we somehow group the numbers so that so can you sort of group the numbers somehow? So maybe or another approach would be something like induction, right? So yeah, so here's another idea. Let's see. Let's okay. Right. So one idea. Yeah, so one thing we can do is we can say what we can look at, yeah, so if we were to induct, we would have to look at the following. We would have to look at n times n minus 1 over 2. Maybe let's put like this. N plus 1 times n over 2 factorial divided by n times n minus 1 over 2 factorial. And we'd have to maybe, we would want for this one to be bigger. Sorry, what do we want? We want greater than greater than what? So yeah. So yeah, so does it make sense what I've done? What I've done is, okay, let's say we were trying to prove that the left-hand side is bigger, right? So what is our goal right now? So we want that the left-hand side is bigger than the right-hand side for n bigger than something, right? That's what we want. And one way you could do that is you could go by induction. So by induction, we would need to compare the ratios for successive n. Right. And yeah, so both of these should simplify greatly. So this one should be, yeah, so this one should be, let's put it like this. Let's say this one exceeds n times n minus 1 over 2 to the power of n. Okay, does that make sense? Because there are n numbers here and they all exceed this one. And this one we should be able to calculate exactly, right? So yeah, can someone tell me what this side exemplifies to?
It's 2 to the power of n times 2 to the power of n minus 1. Minus 1 being not in the power.
To the power of n times to the power of n minus 1, like this?
Yes.
Okay, good. And it's because, so I get, from here I get a 2. I get 2s from all of these. Oh, and then from here I get, okay, I see. Yeah, so you get n 2s and then you get this factor. Is that, or you get n plus 1 2s. This is right. Uh, okay, I think this is true. Okay, good. So the point is, this is what? This is greater than 1/2 times 4 to the n, right? Okay, so maybe what I'll do is this. Now we can look at these expressions. So there's this expression and there's this expression, right? Does it make sense what we've done so far? So the point here is this one should be bigger than this for n large enough, right? Because both of them have, I mean, some n numbers, but the ones here are eventually bigger. Does it make sense what I'm saying?
Yes.
So I'm not going to do the details now because I think this is really not a good use of time. But you see that there's some tricky details you have to understand for which n this will actually exceed this. But the point is, this should convince you that for n large enough, the ratio, this ratio is bigger than this ratio. And then you have to check some small n, right? And so what ends up happening, I will tell you, is that this is true for I think n at least 7. It's true. Okay. And you can prove this. So I don't know if it's worth it for me to do the proof here, but you can prove that for n at least 7, the left-hand side is bigger. And then you check all the small n and see what happens. So does it make sense how you would complete the problem from here?
Is 4 not enough? N equals 4.
Sorry?
Is n equals 4 not enough?
Oh, so you're saying for n equals 4, it's true. So you're saying this one is true for n equals 4.
Yeah, I think.
Yeah, so I think this is true for n equals 4, but there's some base, like, like the base case, like so here's what I mean. So if you go to the previous page that we had, you see for small n, the right-hand side is actually bigger. So you need to compensate for some terms. So maybe it's true for n equals 4, I'm not sure, but I know for n equals 7 at least it's true. Yeah, so maybe it's true for n equals 4, I'm not sure. I mean, maybe we can just check, right? So n equals 4, we get here which equals 720. And here we get 2 to the 4, 15. We get 2 to the 15 times, maybe times minus 2, which is we get 14 times 12 times 8. Yeah, okay, it's true. Okay, you're right. Yeah, so n equals 4 is enough. Okay, good. Yeah, okay, good. N equals 4 is enough. Yeah, so okay, what is the point? If n equals 4 is enough, you only need to check n equals 1, 2, and 3, and okay, that's it. So I think maybe only, I don't know what the solution ends up being. I think maybe it's only n equals 1 or something, or maybe only n equals 2. Okay, but yeah, check n equals 1, 2, 3. Yeah, so does it make sense how you would solve this problem?
Yes.
Yeah. Okay. Good. So now let's go to the next one. So the next one that I wanted to do, was it this one? Maybe this one. Let's do this one first. So good. Yeah, so this is also a short list problem. Yeah, so the problem is to find all positive integers n so that there exists a pair a comma b satisfying this equation, and then there's this sort of strange condition. So yeah, this is kind of weird condition. A squared plus b plus 3 is not divisible by the cube of any prime. So whenever you see a strange condition like this, what it means is probably you'll understand later what the point was. So I'll say at some point later you'll understand the point of this condition. Yeah, so let's take maybe 5 minutes to think about this, and then we can discuss ideas. Okay, so let's reconvene. So does anyone want to share any ideas or observations? I will say with this problem, it's unlike the previous one, it's kind of unclear where to even begin. So what I'll say is we need to do some kind of algebraic manipulations. So that's really the yeah. So sometimes you guys just have to start with some kind of clever algebraic manipulation to even start. Um, Neither side factors, so that's not what I mean. But what I'll say is it's kind of it's a very hard thing to notice, but um, the point here is uh, this term right here is a times b plus 3. Okay, so maybe it's not even right to say that. Okay, so this guy is a times b plus 3. So the idea is, okay, what happens if we um, take this expression and we subtract a. So then this becomes what? Sorry, I wrote the wrong thing. What I meant, sorry, is not a. What I meant is that this one is that's not right. Yeah, sorry. This one is b times a plus 3 is what I meant, right? So what I meant is if you subtract a plus 3. Okay. So now the idea here is to kind of eliminate the b in the numerator. So what does that become? This becomes ab plus 3b plus 8 minus a plus 3 times a squared plus b plus 3 divided by the denominator. Can write this. And okay, yeah. So now it's clear that there's something sort of strange happening, right? So what does this tell you? This tells you this is minus a plus 1 cubed over a squared plus b plus 3. Okay. So what's the idea? Maybe we can rewrite this one as what? As n, no, not like that. As a plus 3 minus n has this very nice form. Okay. So I will say this is kind of a very tricky thing to notice, but let's say we've noticed this. How can we proceed from here, right? So maybe now it's clear what this condition is telling us. So this expression in the denominator is dividing the cube of a number, and it has the property that it's not divisible by the cube of any prime.
Um, Maybe we can say that for every p divides a plus 1, p also divides a plus 3 minus 1.
So for every p that divides a plus 1,
It also divides a plus 3 minus 1.
a plus 3 1? I don't understand.
The left-hand side.
Sorry?
For every p that divides a plus 1, p also divides the left-hand side.
P divides, do you mean a plus 3 minus n? Is this right?
Yes.
Yes, good. Yeah, so yeah, right. So the point is there are leftover primes, right? Yeah, so let's write that. So maybe I can write that more nicely. So there's an observation now that if p divides a plus 1, then p divides a plus 3 minus n, right? Okay. Mm. Mm. Good. And in fact, that tells you that it also divides
2 minus n, or n minus
sorry,
2.
yeah, so it divides n minus 2. Good. Um, hmm. Yeah, the thing that's difficult here is you don't know how many p's, right? So it could be very many p's actually. But let's see. Yes, this is a very good observation. I'm not seeing how to use it. Um, hmm. Hmm. Okay, so yeah, the problem is you can have maybe very high powers of p dividing a plus 1, and then what happens? Oh, but then it's okay, right? So let's see. So yeah, so if p divides a plus 1 once, then yeah, so let's yeah, so this is a good idea. I guess what I'm trying to say is it's even stronger, right? You can I think you can actually argue that a little bit more. I think you can argue that actually maybe a plus 1 divides a plus 3 minus n. Okay. And yeah, so what's the reason? Yeah, so let's maybe start a new page. Yeah, I think we need a new page for this. So let's duplicate. So let's recall everything. So the main point is that a plus 3 minus n equals a plus 1 cubed divided by a squared plus b plus 3. And then the observation is that if p divides a plus 1, then p divides a squared plus b, divides um, divides
-2.
and as well as n minus 2. Good. So and now what I think is even stronger, so let's say conjecture, is that a plus 1 divides a plus 3 minus n. And so how can this go? Maybe we can try to prove it. Let's say p to the k. I'm going to use, oh, that's not what. Okay. So when I write this notation twice, what it means is that p to the k divides it and p to the k plus 1 does not. So it's the exact number of p's. Does it make sense what I'm saying?
Yeah,
Yeah.
I'm familiar with this situation.
So good. So yeah, what does it mean in this case? It means that well, it means that p to the 3k minus 2 divides a plus 3 minus n. Right? Does that make sense?
Yes.
Right. And I think it should be true. 3k minus 2 is greater than or equal to k if k is at least 1. So yeah, this is a proof, right? Does that make sense?
Yeah.
Yeah, so this is a proof that actually a plus 1 divides a plus 3 minus n. So how can we go from there? So okay, now you see it's the same sort of pattern. We've gotten some kind of number theoretic information from prime factorization and stuff, and now we have to think about inequalities, right? So can this even be true? Great, yeah. So we have good. So this is actually proven now. Hmm. And so in fact, it even divides n minus 3, but maybe that's not. So maybe here's one thing, right? Okay, so what's one inequality we can write down from this fact? Maybe even the most obvious inequality. Yeah, so we've shown that a plus 1 divides a number. So there's a very obvious inequality you can write down, which is that a plus 1 is less than or equal to that number. And I think that actually helps us a lot. Do you see how?
But what if a plus 3 minus n equals 0 or
Hmm.
is negative?
Yeah, so what does it, so let's think. So that's a good point, right? but it's equal to this expression, and that expression is positive.
Oh,
Does it make
yeah.
sense? Yeah, so it's a good
Yes.
point. Yeah, it's a good point. It could be negative, and you should think about that, but it cannot actually because of this thing. So, right. So we have this inequality, and it gives us a very, very nice thing. What it tells us is that it tells us this. Did I get the direction right? Yeah, it tells us this, right? Does that make sense? And so already this will give us what? This will give us b is less than or equal to 2a minus 2. Is that right?
Does it not give us that n equals 2?
Oh, you're saying it gives us n equals 2. Yes, how are you getting
Since
this?
n is also positive.
Ah, sorry, say again.
Since n is positive, does that not mean that n equals 2?
Oh, I see. Maybe it's more direct, right? So I see. Ah, yes, sorry, you're right. This actually directly gives us n is less than or equal to 2. Ah, very good. Good. I actually, yeah, I was doing something too complicated. So actually, you don't need this. You don't need this at all because immediately this gives you n is less than or equal to 2. Good. Yeah. So n equals 1 or n equals 2. Very good. Yeah, good.
Actually, n equals 2, so, or yeah, n
Right.
equals 2, since a plus
Mm,
1 is greater or equal to 2.
Great. Yeah. Okay. And actually, n equals 2 because, right, if n equals 1, they're co-prime, right? Yeah. Very good. Very good. Yeah. If n equals 1, then a plus 1 and a plus 2 are co-prime. Okay, good. Yeah. So actually, n equals 2. Good. So actually, that solves the problem. And then, okay, maybe I won't discuss it now, but you still need to give one, you need to find a and b for n equals 2, but that's okay. You just need to find one, a and b, not all of them. Right? Okay, so does it make sense?
Yeah.
Yes. We can just substitute.
Hmm. You're saying to find a and b?
Yes. We just substitute 2 in the original equation.
You're saying, sorry, I don't understand.
Can't we just replace n with 2 in the original equation?
So you're saying we write 2 equals ab plus 3b plus 8 over here?
Yes.
Yeah. And then what do you mean by there's no equation, or?
Yeah. We just, I think we just have to, um, yeah, I'll try to solve the equation.
Yeah. So actually, maybe, I mean, what is the point? So maybe it's actually easier to work here. And so what happens here, we get a squared plus b plus 3 equals a squared plus 2a plus 1, right? I think. And maybe then it's actually quite easy, right? It's b equals 2a minus 2, I think is just what happens. And so that there are many solutions, right? I think I did this correctly.
Yes, I did the same thing.
Yeah. So actually then, yeah, there's many solutions, and it's Should be okay. Okay, great. So now let's see. What is the other one I wanted to do? Oh, yes. So now I wanted to do this one here. Good. So, good. So this is another short list problem. Determine all pairs n comma k of distinct integers, positive integers, for which there exists a positive integer s where Sn and Sk have the same number of divisors. Good. So yeah, so I guess this was on the homework, but let's just recall if some number is factored as like this, and the number of divisors is like this. So are you both familiar with this formula?
Yeah.
Yeah. Okay, good. So yeah, so maybe I'll give 5 minutes and then we can sort of share our ideas. Yeah, so let's reconvene. Any ideas and observations?
Yeah, so if n is divisible by k or is a multiple of k, you can't find such as. So I come to the conjecture that all other pairs are gonna have a suitable s and try to prove that.
Good. Yeah, so if n is divides k or k divides n, with them unequal, then it's impossible. One will have more divisors than the other. So the conjecture is if n does not divide k and k does not divide n, or they are equal, then it is possible. Good. Good. So that's a good conjecture. Maybe any ideas why it could be true? Maybe you tried some small cases or something?
Yeah, and intuitively there has to be like some number that's gonna make the number of divisors like the same using the identity above.
Okay, yeah, good. So somehow it should intuitively be true. Um, good. Yeah, so yeah. Um, how can we do this? Is there any ideas how to proceed with this conjecture? Yeah, so I think the strategy with this kind of problem should be to try some kind of small cases, right? So can someone suggest what case we should try? Like what's the simplest case where we might learn something by trying it?
P to the perfect.
So you're saying n. So when you have to give me two numbers, right? Um,
Two numbers that each has just one prime divisor.
I see. So we're at p to the a and q to the b, right? And p and q are unequal. Good. So now what are we doing? We are saying the number of divisors. I'm going to use sigma for number of divisors. So sigma. So okay, let's write the problem. Want to find s such that sigma of s times p to the a equals sigma of s times q to the b. And now let's make a comment here that we can actually, s could be a lot of things, but we can throw away all the divisors of s that are not p or q, right? All the prime divisors that are not p or q actually won't affect this. Does it make sense what I'm saying?
It does.
Yeah. So basically we can just assume, so without loss of generality, s is like p to the c, q to the d, right? Because we don't need the other primes. Maybe let's not write c and d. Let's write x and y, because the reason I say that is because a and b are frozen; they're given to us, but x and y we can choose. So let's write it like this. Okay. So then I think I want a new page now. So let's let's do this. Let's duplicate this page. We can do this. Uh, yeah. So what does it mean? Um, so yeah, I think it means x plus a plus 1 times y plus 1 equals a plus 1 times y plus b plus 1. And now we want to see, can we make this true? Where x and y we can change and a and b are frozen, right? Yeah. So is it possible? Do you think so? I wrote the wrong thing. I meant b here, right? No, I really meant y, sorry. Uh, the mistake is here. Here I want x plus 1. Good. Yeah, so this time I think I wrote it correctly, right? Yeah, so any idea, can we make this true always?
We could do pick x equals a minus 1 and y equals b minus 1.
Hmm. Great. So then both sides become, yeah, so that works. Both sides now become are 2ab. Good. Okay. Um, good. Yeah. So both sides are 2ab. So that's means our first case works. So do we understand how to generalize, or should we do more cases?
I get it.
Oh, you understand how to do it in general?
Just a second. I'm writing just to make sure.
Oh, okay. I actually don't understand how to do it in general. So maybe it's useful for me if we can do another case. I haven't figured it out. Um, yeah, maybe it'll be useful for me if you do another case. So I don't, because I don't understand yet. Duplicate. Okay. Um, Hmm. 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 So maybe what would be another case we could try to understand what's going on? Unless you both understand what's going on. 'Cause I'm not sure I understand what's going on. Okay, maybe I'll try something like this.
I was thinking of trying um, an that has just one prime divisor and K that has more prime divisors.
So let's try something like this. Uh, so now, um, S is equal to P to the X, Q to the Y1, Q to the Y2. No, but now we need to be careful, right? So, we should be careful because, yeah, we should distinguish one of these primes, right? So we should say this is like Q to the B0 or something. Oh, sorry, P to the B0. Do you understand what I'm saying? Uh, P to the A,
Yes,
P to the B0, right? Because and we have this condition now that B0 is less than A, right? Otherwise, it's not really very interesting. Um, so so now what? Now uh, now we want to say S is equal to P to the X, Q to the Y1, Q to the Y2, Q to the YR. And now, so now it becomes like this. Now it becomes that A plus, let's write it like this. X plus A plus 1 times Y1 plus B1, no, just Y1 plus 1 times Y2 plus 1 and so on, YR plus 1 is equal to X plus B0 plus 1. And now we have Y1 plus B1 plus 1, Y2 plus B2 plus 1, and so on, YR plus BR plus 1. Good, so what can we do now? Hmm. So your idea before was I plug in X equals A minus 1, Y equals B minus 1. And why did this one work? Hmm. Hmm. Okay, maybe we can do something. Maybe we can assume like this. And now oh no, sorry, that's not like this. Okay. And I think the idea is we can make something like this happen. Does it make sense?
Yeah.
Yeah. Um, yeah, we want to make something like this happen, but now we still need to, yeah, so how do we make? Hmm. Yeah, so what's the idea? Um, yeah, so actually I think this will work. So let's see. Let's duplicate. Uh, yeah, so the idea should be what? Now I say, okay, I want this to be true. I have to have y2 equals y1 plus b1. Y3 equals y2 plus b2 all the way to yr equals yr minus 1 plus br minus 1. So what is the point? If we say, let's say b is equal to b1 plus b2 all the way to br, then what we're really solving is x plus a plus 1 over x plus b0 plus 1 is equal to y plus capital B plus 1 over y1 plus 1. Does it make sense?
Mm-hmm.
Yeah. Kareem, does it make sense? Or
Yes.
yeah. And now it's actually the same as the oh no, no, not quite. It's almost. It's yeah, it's almost the same. Well, no, it is the same really, right? Because this is really the same thing as okay, x plus b0. Maybe let's call this one x prime. Yeah, that's the idea. This one, let's call this guy x prime. This becomes x prime plus a minus b0 plus 1 over x prime plus 1 equals y1 plus capital B plus 1 over y1 plus 1. And this is the same as the previous one, right? So I think what was the solution you gave? You gave, I forgot, x prime equals what? Oh, a minus b0 minus 1 and y1 equals b minus 1. Is that right? So yeah, I think this is the one you gave, right, Kareem? This is the one that should work.
I'm not sure, but
Yeah, I think.
it should be the same as the previous case with only one prime
Yeah,
each. So
yeah, it should be the same as the previous case, and I think this is the one that works in that case. Yeah, so yeah, good. Yeah, so doesn't so at least okay, now do you see how you would make it work in the case where n has many primes? All right, so it's a little tricky. So let's
I think yes. We take all primes of k and other than one of them and one of n's primes and remove them all. Then we will have one prime in K and a bunch of primes in N.
So let me understand. So what is the idea? You want to remove primes somehow?
Yes. Um, we can
Um,
do the same the case we did with uh, part of the primes of K and N.
hmm. Yeah, so I'm not sure I understand the idea. Maybe you can try to explain. So yeah, so maybe what should we do? We should so I can start with a general one. And we can assume they have the same primes, right? Oh no, maybe we cannot, right? Yeah, okay. So yeah, so I'm not sure I understand the idea. So how should I do this? Kareem, do you want to try to explain your idea again, or?
Um, yeah. We can, since both of them have at least two prime divisors, we can take one of n's prime divisors and um, all of k's prime divisors other than one,
Mm-hmm.
and by using the second case we tried, uh, we can remove them all, or
Hmm.
yeah, and then we do the same for the rest of the primes we have.
I see. I see. So. Hmm.
But we'll have to pick primes such that we don't get p of to the power of, such that we don't get x is less than b0.
Hmm. Um. So maybe so will it work in some case? Like, what if I write this P to the A, Q to the B, P to the C, Q to the D, right? And we should maybe assume something like maybe something like this. So this is maybe some. Let's assume A is less than B and C is B. No, that's not what I want. We want A is less than C and B is greater than D. So in this case, how will your solution work?
Um, I'll just use the first case. We can
Mm-hmm.
just pick. We can remove p to the power of c and q to the power of b, and then do the same for p to the power of a and q to the power of d.
Mm. So when you say remove, you mean
Yeah, yeah.
yeah, so maybe I'm not sure what you mean by remove.
Cancel. Uh, cancel their. Cancel them in the number of divisors formula.
So something like this. Something like this. Is this right? Or let's see. Okay, so maybe yeah. So let's think. So x plus a plus 1 times y plus b plus 1 equals x plus c plus 1, y plus d plus 1. Um, do you mean something? Do you mean like this or? But it's the same, right? So maybe we can. Okay, maybe I can say one way to sort of organize this whole thing is maybe you can say just in general, right? Um, you can write it like this. So I'm not sure. Maybe it's the same as what your solution, um, Kareem, but maybe we can. It's one way to organize this argument is to write something like this. Um, then okay, and then okay, so you write something like this, and now the point here is I say AI is greater than CI and BI is less than DI. Or maybe I want to say the opposite or something. Maybe I want to say it backwards. Okay, yeah, but yeah, so does it make sense? Now I think it should be right. So what is the point now? Now you are saying x1 plus a1 plus 1 over x1 plus c1 plus 1. Maybe this r is different. BL, QL, QL, DL. And this should be equal to this, right? L plus BL. Um, does it make sense what I've written here?
Um, uh, so I was saying is just we can take P1 um, and all we can take P1 from N, and then we can take all primes from K other than Q1.
Mm-hmm.
And using our second case, we know that we can make the number of their divisors equal. And then we can pick Q1 from K and all primes other than P1.
Ah,
Yeah.
I see. Okay, so it's very clever. Now I understand your solution. It's very clever because we don't need to do all of this. Now I understand your solution. So I see. So no, okay, good. So I guess I'll explain it to myself because I just understood it. So the point is we first do case two, and case two tells us how to treat it when one of the numbers has one prime divisor. And then in the next case, actually, you just do something. Now, this is very clever. Uh, so now, what is the idea? So, no, that's not what I want. I want what? This. I want this. So now, um, what we do is we say, okay, um, we can just assume, right? So we can just assume that it looks like this. Um, yeah. So what are we? And what we're assuming is that assume P and N are co-prime. But now we have to be careful, right? Yeah, let's be careful here. So
We can just assume that P to the power of A does not
uh
divide and Q to the power of B does not divide
yeah, so what
um I'm the opposite. Uh,
uh, the opposite, I see. Is this enough? So Yeah, so your idea is I should pick S1 so that sigma of am I doing this correctly? So sigma of S1n equals sigma of q to the bn. Is this right?
Mm,
Maybe it's not right. So,
S1Q, not and it's not repeating both. S1 is S1n and Q to the B times S1.
right, that's right. Yeah, that's right. Yeah. So S1 q to the b, that's right. And then S2 so that S2 p to the a equals S2 m. But now, so now I'm kind of worried about combining them, right? I mean, so what is S now at the end of the day?
We just multiply them.
Yeah, so now I'm worried that there might be some overlapping primes between S1 and S2. Do you see the concern?
Yeah.
Yeah, so I'm a little bit, I mean, does that is it yeah, so it might happen that yeah, it might happen that yeah, so I'm a little concerned, right? Because so what are the ones you're using? You're using this one and this one. But maybe it's okay. So what's the idea? You need to make sure. Hmm, yeah, here is the problem, right? So um, the numbers may just have the same exact prime factors. Then you will be using all of them in S1 and S2. Does this make sense, Kareem? What the concern is?
Yes.
Yeah. So yeah. So I think maybe it's yeah. So maybe you can fix it somehow, but I'm not sure. Um, I don't know. Okay. Anyway, so maybe okay. How about this? How about this is assigned as homework to finish? Because yeah, we're out of time. Actually, okay. Maybe do you want to keep discussing? I'm happy to spend another 20 minutes and finish this problem. Would you guys like to do that?
It's fine either
Yeah.
way.
Yeah, sure.
Okay, so let's just finish this problem. So now let's see. So I guess we've solved this case with one prime and then many primes. So the next case, I guess, do you want to think about whether there's two primes and many primes, or do you want to do the most general case?
I think we know how we can do this.
Oh, okay. Yeah. So how
We
can you?
can keep choosing one of the P's and one of the Q's and picking an S that fits them. It will
Okay.
divide, yeah, it will only have, yeah, and then when we only have one Q or one P, we can pick that and the rest. Not sure.
So yeah. So maybe how can we do it in? I mean, yeah. Maybe let's have some kind of concrete case. So um, let's say you have something like p to the yeah, something like n comma k equals p to the a, q to the b, r to the c, p to the d, q to the e, c to the f, r to the f. So what can you do in this case?
Actually, I just want to think about it a bit more.
Okay, why don't we do this? Let's give 5 to 10 minutes to think, and then we'll reconvene.
Um,
Yes.
can we just do this for homework?
Yeah, good. So I think that's probably better. Yeah. So uh, let's yeah. So let's leave this for homework. I think it's good if you guys think about this sometime on your own. Um, yeah. So is there anything else you want to discuss before we break? Uh,
I don't have anything to discuss.
okay. Um,
Yeah, same here.
okay. Good. So yeah. So let's break for now.